In this module, we will unravel the science behind solar batteries and charge controllers, exploring how they store, regulate, and maximize solar energy to keep systems safe, smart, and sustainable. Storage and control devices. In many regions, off-grid solar applications remain essential, especially in the rural areas where electricity from the state Discom's grid is not available in the evenings because of enhanced load in the urban areas and limited availability of power with Discom. Core components make these systems viable. 1. Energy storage and 2. Control devices. Energy storage, typically through batteries, ensures that solar energy generated during the day can be stored and used during the night or cloudy periods. The control devices, primarily charge controllers, regulate how energy flows between panels, batteries, and loads. Energy storage system battery. Batteries are at the heart of solar PV energy storage systems. They store excess power from solar panels and release it when sunlight is unavailable. In other words, surplus solar power, after catering to the consumer's load directly during the day, gets stored in the battery energy storage system. Different types of batteries offer various performance characteristics suited for specific applications. Types of batteries. Batteries are classified into primary and secondary types. 1. Primary batteries are single-use, alkaline kind, and not rechargeable. 2. Secondary batteries, such as lead-acid and lithium-ion types, can be recharged multiple times, making them suitable for solar PV systems. Major types of secondary batteries used in solar power systems are 1. Lead-acid. 2. Lithium-ion. 3. Valve-regulated lead-acid, VRLA, maintenance-free batteries, which are quite popular in the industry as they are cheaper than Li-ion batteries. Battery characteristics. Battery performance depends on parameters like depth of discharge, DOD, state of charge, SOC, voltage, and storage capacity. These metrics determine how efficiently a battery stores and releases energy. 1. Depth of discharge in case of lithium-ion batteries is up to 80%, which means that 80% of the battery capacity in terms of energy can be discharged. 2. Rate of charging in case of lithium-ion batteries is considerably high. Batteries can be fully charged within 2 to 3 hours. The biggest advantage of high rate of charging of a lithium-ion battery system is that the battery energy storage system, BESS, can be charged every day to its full capacity during the daylight hours. Effective temperature. Extreme temperatures can impact the performance and lifespan of the BESS. The ideal ambient temperature for a lithium-ion battery system is between 15 deg Celsius to 40 deg Celsius. Operating outside this temperature range can negatively affect performance and lifespan. Extreme cold slows ion movement, while high heat accelerates degradation and increases the risk of thermal runaways, which means that the heat generated within the battery exceeds the heat loss to the environment, leading to a dangerous state of rapid overheating, fire, smoke, or explosion. Specific energy density. This is the energy stored per unit mass of the battery. In case of a lithium-ion battery, energy density typically ranges from 50 to 260 watt-hours per kilogram, though advanced versions can reach up to 300 watt-hours per kilogram, or even more, up to 1,000 watt-hours per kilogram. Higher specific energy density means more power storage for the same weight or volume. Determination of BESS capacity. The sizing of the battery energy storage system, BESS, for a solar power system is of very vital importance and highly crucial for the successful operation of a solar power system. An in-depth study is required encompassing various parameters to arrive at the correct solution for its optimum functioning during real-time operations. In a typical solar power system, the sizing of the battery system depends upon the following factors. Daily energy consumption. This is the most critical factor, representing your total daily energy consumption in kilowatt hours, kWh, that needs to be met from the batteries. You must calculate this to know the minimum amount of energy the battery needs to store to meet your needs on a daily basis. Days of autonomy. This refers to how many days you want your system to run without any solar input. A higher number of days, for example, 2 to 3 days is standard for off-grid, requires a larger battery capacity. especially in areas with inconsistent sun. Depth of discharge, DOD. The DOD is the percentage of the battery's total capacity that can be safely used. Batteries with a higher DOD, like lithium-ion, can be discharged more deeply, meaning they can have a smaller physical capacity for the same usable energy compared to batteries with a lower DOD. Battery chemistry and type. Different battery chemistries, e.g., lithium-ion versus lead-acid, have different energy densities and performance characteristics, affecting their overall capacity and how much of that capacity can be used. Solar panel system size and efficiency. A larger solar array can charge batteries faster. The efficiency of the panels and the number of peak sun hours in your location directly impact how much energy is available to be stored. Environmental temperature. Low temperatures can decrease a battery's usable capacity because chemical reactions inside it become slower. Inverter efficiency. Some energy is lost during the conversion from DC to AC power. You need to factor this loss into the calculation to ensure the battery is sized correctly to compensate for the inefficiency. System voltage. The battery's voltage must be compatible with the inverter voltage. Battery capacity in watt-hours. Discharge rate. How fast you draw power from the battery affects its capacity. A high discharge rate can reduce the total energy you can pull from the battery compared to a slow discharge rate. Budget. The initial investment, installation, and maintenance costs are practical factors that influence the final battery capacity you choose. In a nutshell, a very fine balance is to be made between the energy requirement during non-sun hours, PV capacity of the plant, charging rate of the batteries to meet up the demand, system voltage, climatic and environmental conditions of the location, and depth of discharge for determining the battery capacity. Performance characteristics of batteries. Lead-acid and lithium-ion batteries differ significantly in how they perform. Lithium-ion batteries have a longer cycle life and higher energy density, while lead-acid batteries are more affordable but heavier and require more maintenance. Interconnection of batteries. Batteries can be connected in series to increase voltage or in parallel to increase capacity. Proper interconnection ensures balanced charging and reliable power delivery. This depends upon the requirement of desired system voltage, and accordingly the circuitry is decided. Each bank of the batteries conforming to system voltage is then connected in parallel to build up the required capacity of the BESS. Standards certifications. To ensure safety and quality, batteries must comply with international standards such as UL 1973, UL 9540, IEC 61427, IEC 60086, and IEC 62133. These certifications cover design, performance, and safety aspects. Solar charge controllers. Charge controllers are intelligent devices that regulate how solar energy charges batteries. They prevent overcharging, over-discharging, and extend battery life by managing voltage and current levels. A solar charge controller is a device that regulates the voltage and current from solar panels to prevent damage to a battery bank. Its primary functions are to protect batteries from overcharging and over-discharging, which extends their lifespan and ensures the efficiency of the solar system. It also manages the power flow to electrical loads and can prevent the battery from discharging back into the solar panels at night. Key functions of solar charge controllers: prevents overcharging. A solar panel's voltage can be higher than what a battery needs, so the controller regulates the power to prevent the battery from overcharging, which can cause damage. Prevents over-discharging. It can disconnect the load from the battery when the battery's voltage drops to a certain low level, which prevents damage from over-discharge. Manages power flow. It directs power from the solar panels to either the battery or the electrical loads, ensuring optimal energy management. Types of controllers: maximum power point tracking, MPPT. More efficient, especially in varying conditions, as it finds the optimal voltage for maximum power output from the solar array and converts it to the correct battery charging voltage. Pulse width modulation, PWM. A simpler and less expensive type that connects the solar panel directly to the battery and uses a series of pulses to regulate the charging process. Types of solar charge controllers. Charge controllers come in single-stage and multi-stage types. Multi-stage controllers are preferred in modern systems, as they optimize battery charging through bulk, absorption, and float stages. Comparison of MPPT and PWM chargers. MPPT and PWM are two key technologies in charge controllers. MPPT controllers continuously track the solar array's maximum power point for optimal energy harvest, while PWM controllers regulate voltage using pulse width modulation. Although PWM is cheaper, MPPT delivers better efficiency and energy yield and, therefore, technically significantly superior and prevalent. 1. Handbook for Rooftop Solar Development in Asia, Asian Development Bank. 2. Best Practices for Operation and Maintenance of Photovoltaic and Energy Storage Systems, NREL. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.